welcome back to another video. In this video, I'll be discussing powers and roots, and many people do find this a tricky part of GCSE mathematics, but hopefully if I do clarify this, it becomes a lot easier. So to start off, we'll have the 7 easy rules that you should keep in mind. So let's go. The first one is about multiplying powers. And when we multiply these powers, for instance, 3 squared times 3 to the 4, what we do is we add these two powers. So now we're going to get 3 to the 2 plus 4, which is 6. So it's 3 to the 6. And often in algebra, you'll be dealing with variables. And in this case, we can always swap the numbers with the variable form. So like a squared times a to the 4, that's going to be a to the 6. And you can always use this rule whenever the base of these are the same. So you can see how these two are 3, how these two are a, right? And why is this the case? Well, if you do remember what powers represent, it's just repeated multiplication, right? So we have 3 times 3, and I'm going to put this in brackets, hopefully make things easier to see. We have the times, and 3 times 3 times 3 times 3, 4 times. And obviously, we don't distribute these brackets because these are multiplications, right, rather than additions. So in order to simplify this, it's actually very easy. We just strip out the brackets. So we're going to get 3 times 3 times 3 times 3, 6 times, and that's why we get 3 to the 6. The next rule you should remember is very similar. It's when we divide. And maybe you can guess it already, but when we have 3 to the 4 divided by 3 squared, we're going to subtract the 2 powers. So we're going to get 3 to the 4 minus 2, which is then 3 squared. And similarly, you can use the same logic as when we have a's or b's or any variables. The same rule still applies, right? And this is, again, we can prove this just by remembering what powers represent. So we end up with like this, but again, since we can cancel these, so let's cancel, and we're left with 3 times 3, which is, of course, 3 squared. To the next rule, which is raising powers. And for instance, if we raise 3 squared to the 3rd power, or in other words, we cube 3 squared, what we do is we multiply these 2 powers together. So rather than adding or subtracting, we multiply, right? And we're going to end up with 3 to the 6. Again, if you want a way to visualize this, what this really represents is we're going to have 3 times 3 times 3 times 3 times 3 times 3. And so in each bracket, we're going to have 3 times 3, which is a total of 2 times because of the squared, right? And we also have 3 of these brackets because we cube this. So we want to repeat the multiplication by itself 3 times. So this happens all in all 3 times. Okay. The next 3 rules aren't necessarily operations like this. They're just things that you have to bear in mind. So for instance, when we raise anything to the 1st power, we're going to end up with itself. So like x to the 1 is x, 3 to the 1 is 3, 4 to the 1 is 4. And again, the way to demonstrate this is we can use the dividing rule in a sense. So for instance, when we have x to the 4 divided by x to the 3, this brings us with x to the 1, right? But if we do visualize this, what this really looks like is x times x times x times x over x times x times x. So again, we can cancel this, we can cancel most of these until we're just left with a single x left. And hopefully from this you can see that it doesn't matter what the base of the power is. After cancelling them, you're always going to end up with one of these bases left. You're always going to end up with x or a or 3 or 4, so it doesn't matter which one's which. Okay, and following upon the last rule, and when we raise anything to the 0th power, we're just going to get 1. So like when we have x to the 0, that's going to be 1. 3 to the 0 is going to be 1. 4 to the 0 is going to be 1, and so on. And the only exception that you have to keep in mind is 0 to the 0. And that is actually undefined. And again, we can use a similar argument to what we've done before, right? So, for instance, let's have x squared minus x squared, which, from our knowledge of the divide, when we divide powers, that's going to get us x to the naught, right? We've subtracted these two powers. And what does that look like? Well, that is x times x over x times x. And hopefully you'll see that it doesn't matter which base you have, at the end of the day, you're going to cancel all of them anyway. And after that, you're just going to end up 1 over 1, which is 1. Right. The next thing you have to keep in mind, when we raise 1 to any power, that is 1 cubed, 1 to the 4, or even 1 to the x, that's always going to be 1. And hopefully you can just tell right away why that's the case, right? Because when we multiply 1 by 1 by 1, at whichever amount of times, the 1 is going to be left unchanged. Finally, we have when we take roots, or we take powers of fractions. So let's have 2 over 3, and let's cube that. What we do is we cube both the numerator and the denominator. This actually derives from what we know about multiplying fractions. And we know that when we multiply fractions, we multiply the top and bottom, right? So this is the same thing as this, which then is now 2 cubed over 3 cubed. And if you do want to expand this, this is now just going to be 8 over 27. Okay, and let's keep going. Let me start a new page here. So then we have 3 more tricky rules. And these three rules are the ones that most people find it hard to understand. And hopefully I can show you that maybe that's not the case. Okay. First thing we've got to keep in mind, when we take a negative power, that is 3 to the minus something, or 4 to the minus something, right? We're going to get 1 over 3 squared. So what have I done here? Well, what I've done is I've taken the base, I've put it as the denominator of a fraction, and I've swapped the signs. Okay, so 3 squared is the same thing. 1 over 3 squared, sorry, is the same thing as 3 to the minus 2. Another example, 4 to the minus 3 is going to be 1 over 4 cubed. Okay, why is this the case? And I think I've abused this argument way too much, but it just works, right? So let's say we had 3 to the 1 divided by 3 to the 3. This is the same thing as 3 to the minus 2, and I think you might already see where I'm going with this. Right, after cancelling one of these 3's, we can't cancel any further on the numerator. But realize how we're left with 2 of these 3's as the denominator. And then, so from this, you can see that this is why the numerator is always going to be 1. After you've cancelled everything, you're going with this logic, that is, after we've cancelled everything, you're going to end up with only numbers at the bottom, right? And it's just so that happens that this is 3 to the minus 2 is going to be 1 over 3 squared. The next thing we have to keep in mind, when we have, let's do 16 to the 1/2, right? And don't let this fractional index scare you. There's nothing too outlandish. This is actually just the same thing as the square root of 16. When we have, let's say, 8 to the 1/3, this is the same thing as the cube root of 8. And from here, maybe you can see the pattern already. We simply just take the root of whatever this bottom of the fraction is. And I want to show you something that might help you. So let's say we're going to multiply the square roots of 16. Well, what is this? This is just going to be 16 as the definition of a square root, right? We multiply the square root of itself, we're going to get that number. Well, likewise, if we're going to do 16 to the 1/2 times 16 to the 1/2, you can see that when we do add these powers together, because we've proven how we multiply powers before, this is the equivalent of saying 16 to the first power, which is, as we know, 16. And hopefully you can see why these two are equivalent. From then on, just give a few more examples. Let's say 2 to the 1/8. That's just going to be 2 to the 8th root of 2. Finally, this brings us to our last rule. That is, if we have a fractional power that looks something like this, in which case 16 to, let's say, 3/2. And to do this, what we do first is we can deconstruct this. That makes things a lot easier. What I mean by this is we can change this into 16 to the half power cubed. And we've actually done the opposite of this when I've raised the power to another power previously. Remember that this is equivalent of multiplying these two powers together. Well, I've done the opposite of that. I've now split this up. But maybe this is easier to see because knowing what I've said here, this is actually going to be the square root of 16 cubed. Well, actually, I'd advise writing square roots like this because it doesn't really help us and it doesn't allow us to use the indices rules that we've learned. Rather, when we keep things like this, we can manipulate indices more easily by using multiplication, addition, division, and stuff like that. Also, I'd like to point out that this has the order of this does not matter. Actually, this is just the exact same thing. Okay, because at the end of the day, if we do multiply these two numbers, we're always going to get 3 halves. But actually, with that being said, I do think that the first way is much easier if you want to compute this mentally, because we know that you can square root 16 very easily, and that's just going to be 4. And if you do cube 4, that's going to be 64. And that's easier to do mentally rather than cubing 16 and then taking the square root of that. So in the case you have a calculator, it doesn't matter which way you do it. In fact, you can just input this down in your calculator and you get the answer. But if you are doing this mentally, then there are clever tricks. You just try to see which one's easier to do first, and that'll help you.